So there's a group of paradigms at which you could approach different kinds of problems, and here's a kind of simplified list of those. And they break into two halves. There's supervised learning, where we as humans help to guide the computer. We give it examples and tell it this is the right answer that you would expect, and it learns from those right answers. And then there's unsupervised learning, where we just give the computer data, and it has to discover its own insights and its own ideas from the data without any guidance. Now, supervised, I'll show examples of these in a minute. I break down into some typical tasks of classification. I can give it examples of things that are in different classes. I can say, here's a picture of a cat, and here's a picture of a dog, and then it wants to learn how to recognize a future picture. Is that a cat or is it a dog? Prediction is similar, but we're trying to get numbers out. So we're saying, if I tell you something about, give examples of people's lifestyle, can we predict their IQ or their income? We want a number out that is rather than discrete classes. And the other group I'll show examples of a sequence prediction, what happens next, where things are ordered and we want to be able to predict the next element of a sequence. On the unsupervised side, I'll show you some examples later of creating clusters, automatically grouping things together that have something similar about them. And another area of research right now is reinforcement learning, but that's beyond the scope of what we'll show in these videos. So let's take the first of those. Let's look at the task of classification. I'm going to start with the most trivial example that I can. I've got some data with just 4 data points. And here's my training data. This is supervised, so I'm going to tell it the correct answer, that an input of 1 is going to be in the class of A, and so is 2, but 3.5 is going to be in the class of B, and 4 is going to be in the class of B as well. So in the Wolfram language, I press Shift Return here to teach to execute this line and to teach the computer what it needs to know about that data. And then I ask it to classify that training set. And this is where the Wolfram language really jumps in and helps, is that I haven't had to say anything more than the task that I'm trying to achieve. And it's produced a classifier function, which I've stored in this symbol here. And that now allows me to apply that new function that it's just invented. It's just created a program for me that I can apply to data that it hasn't seen. So I can, for example, say, what class do you think 1.2 would be in? And given the experience that it has from this data here, it's made a prediction. It says, I think that's in class A. So it's learnt that from the experience it has from the data set. And we can drill in a little bit further and ask for things like, what are the probabilities of the different classes? And we can say that it feels, from the data it has, as confident as it possibly could be. It's essentially 100% probability that it's A, and a minuscule probability that it could be class B. And now that, of course, is based on the data, so it's got nothing to contradict this example, which is why it doesn't have any doubt. It's not a quantification of the reality, it's just a quantification of the consistency of the data. So let's look at some slightly richer example than that, and let's try it with some different kinds of data. In this first example, I had numbers in and classes that were strings. Here I'm going to put pictures in, and I'm going to get classes of night and day. So the outputs are going to be strings as well. If I make this a little larger, you'll see that this is a photograph of some nighttime street scene. But you can see, because of the automation, the way that I access this is exactly the same thing. I just say classify, that's my task, and here's my list of data with my inputs and outputs. And the fact that those are photographs is automated by the system. So I've now built a new classifier function called day-night, and I can now apply it to images that it hasn't seen. It's very important to test on images it hasn't seen, because it should always do a good prediction on images that it has seen, but that's not of any use really. We could just match things directly. What we really want is that we see predictions being useful when we have new data. So we can see here the 6 pictures I just gave it, and the first 3 is decided were daytime, and the last 3 is decided are nighttime. Now the features that it found, that's not really our concern. Our concern is only, did it do a good job of making that selection? So now you already know how to do classification. Let's talk a little bit about how that works. There are quite a few different methods for achieving the same task of classification. And to illustrate this, I've got another trivial set of data. This time I've got some 2-dimensional values, some XY values for input, and my outputs are going to be some colors. And I can build a classifier function from that. which puts it into 3 classes, and then try it on some unseen value, and it makes a prediction that at 1, 1, it's expecting it to be green. So I've just set that up to illustrate the different methods in action. So here's the original data plotted out, and we can see that there are sort of groups or areas that appear to be green and blue and red. And then there's a question of can we predict what's going on in between? And as a human, you might expect, well, this is probably going to be green. And I've solved the problem here in using six different very standard methods, and I'll just walk you through each one and what they're trying to achieve. Perhaps the simplest and one of the most robust is nearest neighbor method. Here's the predictions that it makes. I've asked it for what it thinks at every particular position, but the basic way that nearest neighbors works is that if I choose a point and I want to make a prediction, it looks for the nearest neighbor to that point. So for this point here, the nearest neighbor is a green point, so it's probably going to be green. Now, there are more sophisticated variations where you look at a whole collection of nearest neighbors and then infer something from the collection rather than nearest, but the very simplest is just to look at the very nearest neighbor and assume that that tells you something about the point. Now, of course, one important thing to realize is that my examples here are trivial in terms of dimension. I've got 2-dimensional data and 1-dimensional is all I've done so far. Where these methods start becoming really useful is when you have many dimensions. You have maybe 10, 20, 30, 100 different bits of input information, and then you have to think in terms of this sort of very high dimensional space, what's the nearest point in a 100-dimension space. It's a lot easier to visualize in 2D though. So another method, and here's the result from it, is logistic regression. Really, that's just a fancy collection of fits. We're fitting to logistic sigmoid functions, and they have a nice characteristic of being a curve that goes from 0 to 1. So it's a very continuous way of saying true or false in a way. And by fitting a collection of those functions, you get a much smoother boundaries very often, and some level of how much you've crossed a boundary. Support vector machine, again, fairly similar results from all of these methods. That works on the basis of taking the group of data and trying to split it in half across a plane. So imagine trying to draw a line, if we go back to the data, that most successfully partitions the points. You might draw a line across here, and that would partition off all the red points, and another line across here, and that would partition off all the green points. And that's essentially what it's trying to do, is recursively subdividing by cutting the plane in half. Of course, like most ideas, the idea is simple, but in practice it's been made much more powerful by transforming the space so you get curvy splits rather than straight lines. But the idea is essentially just partitioning the data. Random forest method isn't terribly dissimilar. It works by making random choices of splitting the data. So we might randomly split at x equals 4 and put a split down this line, and then randomly split at y equals 3, and then it looks at how well it does to make a prediction. And then it repeats randomly, and it does it over and over again until it stumbles on a good way of splitting up the data into the different partitions. Again, there are ways to try and accelerate that, but that's the basic idea. Naive Bayes is a bit more limited, but has great applications in things like spam filtering. And the basic idea of naive Bayes is to assume that the different variables are basically independent. The last one is the most complex. We'll come back to this properly in the last video in the sequence, is neural network. It really is just fitting in regression again, but it's layers of fitting one upon another. So it's supposed to mimic the way the human brain works, that one set of neurons will try and do fits to a certain characteristic, but above them another neuron will take in the outputs of those neurons. So if you take, for example, say an image recognition problem, you could imagine that at the simplest level there are neurons that are recognizing lines or brightness or patches of color or basic texture, and above that you have neurons that aren't looking at the image anymore. They're hearing that something's got lines and corners and curves and taking that information and fitting a model to that. It turns out to be a very powerful set of methods, but a little bit richer and harder to control than the others. We'll talk about that properly later. So with all these different methods, one question is, which one do you use? And here there's a mindset change that one has to make if one's coming from a classical modelling approach. In classical modelling, you tend to build a model that somehow describes the physics or the reality of the situation that you have data from. So if it's a physics example, you start thinking about equations of motion or differential equations, and you build a model that somehow represents what you expect to happen, and then you fit the data to it. And that's got a very powerful outcome that the fits that we get somehow tell us about the reality. We can learn things from the model itself, as well as be able to make predictions from it. The machine learning mindset is a little bit more along the lines of the black box. We don't really ask the question how it works, and the parameters that we get out of the fit aren't actually terribly useful in just telling us something about the physical reality. The question is only, does it work? What we need is a model that gives predictions, and we don't really care how it works or what's inside the black box. So with that approach, one of the key methodologies that one wants to take with machine learning is to split the data. You're obviously going to get the best fits by using the most data. The more data you have, the more you can tune the parameters. But what you always want to do is to hold back some of the data for testing. And so the concept is that you train on maybe 80, 90% of the data, and then you hold the 10% back for which you know the correct answers and see whether or not your model predicts those answers well. If it predicts well, it's a good model. If it doesn't, it's not. So let's walk through that workflow a little bit. I'm going to load a classical machine learning data set here. These are 4 measurements from a collection of flowers. I'm not quite sure what the measurements are. Perhaps they're length of petals, length of stem, things like that. But we have 4 pieces of input. And then we know from the data set that was collected which of 3 or 4 different types of iris this particular data point represents. So this one was a setosa, whereas if we look further down the data set, these measurements were from an example of a virginica. So that's our data set. Let's just hide the data here. We don't need to see it. And I'm going to sample that and take out a random sample of 100 of those. So there's 100 of the data points. We had about 120 to start off with. In fact, we could just check that here. We could just ask for the length of the iris data, and we'll see that actually there was 150. So I've taken 2/3 of the data set. And I'm going to now make a test data set, which is the complement. So all of the ones that aren't in my training set. So there's my other 50 data points. Now I'm going to take the, and I can test that those are in fact non-overlapping, which is very important because you never want to test with the examples that have been seen. So we can see the intersection between those sets is an empty set. So we've successfully partitioned the data. So now we'll do what we did before. We'll ask for the automation to classify that. And we've got our classifier function. And now we're going to measure the performance of that against the data which we held back. Now the Wolfram Language has a convenience function for doing that, which will do a whole bunch of measurements all at the same time. And it produces this measurement object which we can interrogate. So if we look at the measurements, we can see the accuracy, which is really the kind of headline figure that we're usually chasing, is 90%. So that means out of the 50 test data points that we kept back, 9 out of 10 it made a correct prediction about what kind of iris it was. Now, of course, whether that's good or bad is very contextual. For identifying flowers, I think 90% is pretty good. That's probably better than having to have a botanist go and do it for me. If that was detecting cancer from a screening process, well, that's probably not very good at all. If this was some safety critical system, which, to be honest, machine learning is not really good for safety critical things like running a nuclear power station, then 90% accuracy on what to do next would be an absolutely disastrous number. So one has to think about the context to decide, are we satisfied with that as a performance? Often the test is it better than a human, or how does it compare to a human? There are other ways we can dig deeper in as well to try and understand how we can improve. For classification, one of the easiest to look at is this confusion matrix. And that's looking at class by class, the inputs that we had, the outputs that we were predicting. So let me explain this diagram here, if we go through it a little bit at a time here, that on the left-hand side, we've got the actual class in the data. So there were 17 setosa examples in our test set. And out of that, the output, it predicted setosa 17 times. So it got 100% of the setosas right. And we can see here that it's got none in the misclassification. And versicolor in, it incorrectly identified 2 of those as Virginicas, and didn't get any wrong as setosas, and got most of them right as versicolor. So the quick way to interpret this is we're looking for a nice, strong diagonal line. If everything's on the diagonal, that's perfect prediction. But what we're wanting to see that the headline accuracy doesn't tell us is where it's going wrong. And we can see that there's some confusion between versicolor and Virginicas is where the errors are coming up in, and that seems to be fairly symmetrical. It occasionally just gets confused between the 2 in both directions, but it's pretty good at the setosa. And then we could go a little bit further and say, well, let's look at the best and worst classified examples and say, does that tell us something? Maybe I can go back to the original data and check the example, and perhaps it may be that it was incorrectly classified in the original data. Or we find that it does a very good job only on tall plants but not on short ones. So we can start drilling in through this sort of search for best and worst in order to try and figure out, if we collected more data, where do we want to concentrate, for example. And there's a whole bunch of these things, which different ways of looking at accuracy that I don't really have time to go into now. So there's about 30 different methods for measuring, but for me, the one I always look at first is simply the accuracy. So one thing that I've kind of jumped over and not pointed out as we go along, if I go back to one of the original examples here, we did this classification of colors. Buried in the small print of this object that came back is the method that it's chosen. So even though there were lots of methods for classification, one of the things that the automation of the Wolfram language does is to select which method is most appropriate. And in this case, it's chosen logistic regression. So the question is, how does it go about that? Well, the basic idea behind it, the sort of optimization that it tries to achieve, is it starts classifying by all of the methods, and then it sees which one is performing best, and then does the full work to classify against that method. Now, in these examples, there was so little data that, in fact, you could just classify completely by every single method and then measure which one does best. But if we had megabytes or gigabytes or terabytes of data, then we might have training times that are quite significant. And so training on a few thousand data points and then seeing which one is starting to make reasonable predictions is the basic method for deciding where to go next. And then you spend the real effort on the one that shows most promise. But in the end, getting that best is a trade-off of time and effort versus accuracy. You always want to do it as high a quality as possible in the time that you have available to you. So, before we go on to other topics, let's look at a few slightly less trivial examples. And I've brought a few fun examples here with me of classification in action. So here's a tool that I built that is just behind the scenes using Classify, and I'm going to teach it from scratch how to play rock, paper, scissors. Well, not how to play, but how to recognize. So the idea is that I'm going to give it some examples. So this is my rock fist, and if I put it onto rock here, and it's going to start capturing images, and if I move this around a little bit, get maybe 10 or 15 images, and then when we've got some of those, we'll show it what paper looks like, and we'll capture some of those. And then when we've got enough of those, we'll do some scissors images and capture a bunch of those. And I think once we're at about 40, we can stop. And now we're going to run the classify function on that data. So it's now training the classifier. And now we can put it into watch mode, and we'll watch the webcam some more. And now it thinks my head is a rock, but if I hold up a rock, it says rock, paper, scissors, and you can see it's already in a fairly small amount of data doing a good job at recognizing what I'm showing. But actually, if we look at the code behind the scenes on this, you'll see that the entire training button just is calling the classify function that we've been talking about already. All of the rest of this code is just interface creation to set up the checkboxes and capture the camera and to not capture too many images too fast. Now, of course, that's a fairly small amount of data, and it's done quite a good job, but partly because it had a consistent background that it didn't have to worry about. In order to get robustness, you need a lot more data. So we we have a classifier that we've pre-trained on about 150,000 ImageNet images, and so I've got that attached now to this streaming cam, and we can see it's seeing a person in the image. But if I hold up some objects here that are on my desk, we can see that it can recognize all kinds of objects from the pictures. But that has taken tens of thousands of examples, so that it has examples of tea urns and teapots and mugs and people, and takes considerably more training time. Even GPU accelerated it several hours of training time, although you can see the execution time is near instantaneous. And perhaps we've got time for one more example. This is just taken from a recipe website where we scraped in a whole bunch of recipes, and they were categorized according to international cuisine. And so by just stripping out the ingredients list, we made this classifier, again just running the classify command, and the idea is that I can put in some ingredients like potato and cabbage and divine cuisine, and it can use that classifier to give the probabilities that this is probably an Eastern European dish if it's made out of just potato and cabbage. But if it had, say, rice and chili in it, then it's more likely to be East Asian, with various diminishing probabilities of being other regional dishes. But in the end, all of these are just examples of trained, supervised training on classes, where we're trying to say what kind of a thing is this out of some known experienced classes.